So we start into this thing. We said that A and B to be positive. So this is the condition of the initial value into the existence, this existence and uniqueness theorem. And we say, and the properties, the problem with this existence and uniqueness theorem, it does not specify for you. It says for some, but does not say what for how much you think is for some. Like it's gonna be for some A and B, but how big is A and B? It does not satisfy. And also notice that this theorem works like this. So it tells you that if those things are satisfied, that there exists a unique solution. But if those things is not satisfied, it doesn't tell you anything about the existence and uniqueness theorem. Let us take an example. Take an example of y prime minus sine of x and y is equal to 0. So let's walk through it. First thing we want to write it in the form of y prime is equal to some function of x and y. So you can write that y prime is equal to sine of x and y by adding sine to both sides. So give you y prime is equal to sine of xy. The second thing, this is the function. This is the function of concern, sine of x and y. The theorem tells you take the derivative with respect to x. So the partial derivative with respect to x of sine of xy is equal to y cosine of xy. In other words, just treat y as a constant. So the derivative of sine would be cosine, and use the chain rule to get that to treat this thing as a constant. So it will be y times cosine of xy. And right now differentiate the function with respect to y. You get x cosine of xy. So for this function, those two functions are continuous everywhere. So if the initial value problem was 3 and 3, we can say for sure for this interval that there is a unique solution. However, we cannot say how big the interval can be. Let me again see you the picture of what I'm talking about. So imagine that this is a function. It says you okay, and this is some kind of the initial value problem that is here. It tells you okay, over this interval there is a unique solution, and there is a unique solution. So there exists a uniqueness. But it did not tell you anything about what's happening outside the box. So you only actually didn't know that thing, you only know what's gonna happen inside this box. So you know that inside that box, if I worked hard, I'm gonna find a solution, and it's gonna be unique. And you don't know how big is the box. So that's the problem of this existence and uniqueness theorem. We're going to see that in the next example. So in the next example, y prime is equal to y squared. I give you the differential equation like this. Y prime is equal to y squared. So let's apply the existence and uniqueness theorem conditions. First thing, take the function, differentiate with respect to the function. Let's tell g of x, y, let's be clear, is equal to y squared. Applying the existence and uniqueness conditions. If you differentiate with respect to x equal to 0, because there's no x. You're not going to use chain rule because this thing is actually like a function two independent variables. So for x it's going to be 0. Let's differentiate in terms of y. It's going to be 2y. And let's put the initial value problem as y of 0 is equal to 1. So we get two functions. The first function we call it h of x and y, or whatever you want to call it. This is the first function. And this is the second function of x and y, will be 2y. This function is continuous everywhere, and this function is continuous everywhere. More importantly, even though if the function was not continuous somewhere, for example, imagine if the function somehow was x minus 6. This function is not continuous at x equal to 6, but the theorem does not say anything about x equal to 6. It does only care about 0 and 1. X equal to 0, this thing is always continuous. This thing x equal to 0, this thing is always continuous. So it does not matter. We are just focusing on 0 and 1. So those are the two important things. After this thing, okay, this is the two things that we understand. So we know that there's a unique solution in that region. There's existence and there's uniqueness. So for my notes, I know the solution is y is equal to 1 over 1 minus x. I found that this is a solution. Let's check that this is a solution. The derivative, if you differentiate this thing, it will give you y squared. Let's differentiate it. Over here, this is small box. So if you differentiate this thing, it will be negative because you can using the okay. I'm gonna do it in detail. So d divided by d. I'm going to do it fastly. Then I'm like, oh, I'm smart. And I'm gonna do it in details. So this is the thing. Y is that. So y is equal to write it as 1 minus x to the negative 1. dy divided by dx, but the power rules. You just put that thing down, subtract the power, comes down, and differentiate what's inside, become negative 1, so 1 minus x, all squared. Well, it's equal to the y squared, because if you square this thing, it's going to be equal to that thing. So we actually found that this is actually a solution for the problem, and for the value of 0 and 1. Let us see if it's actually a solution for all value of x. It's not, because if you put x is equal to 0, you get something. You get that this thing will be 1 over 0, which is undefined. So we cannot say that this is a solution. We cannot say that. So the theorem guarantees the existence and uniqueness at x equal to 0, y equal to 1. But at y equal to 1, at x equal to 1, the solution does not exist. So the theorem does not say anything about the values. Even though both of those functions are continuous everywhere, yeah, it doesn't matter. Both of those functions are continuous everywhere. However, there is still the problem at x equal to 1 that there is no solution at x equal to 1 that satisfies this initial condition. Let's just think about it again. There is only one unique solution, the one function that satisfies this initial condition, which is this solution. However, this solution does not exist. This solution does not satisfy the differential equation at x equal to 1, because you will end up with the 1 divided by 0. So the theorem is a local statement theorem, which is the bad side of this theorem. So this is the bad side of this theorem. Next video we're going to see a stronger version of another theorem that's actually stronger than this theorem, and we see how we're going to use it to see, but that theorem only applies in a linear first order for now, ODEs.